Atmospheric circulation is driven by more than just large-scale cells that are being driven by rising and subsiding air. Circulation is also redirected by the rotation of the Earth itself. And here, we're going to cover what's called the Coriolis effect. Earth's rotation causes winds to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. And this is not because the Earth rotates underneath them. Instead, it's due to angular momentum. This here is the equation that covers angular momentum. So angular momentum is equal to the mass of an object, its velocity, and then r here is the radius of rotation. And essentially, if the mass of a parcel of air remains constant, its velocity is inversely related to the radius of the rotation. And so if this is the Earth here, and here's the equator, and a parcel of air moves north, then as it moves north, that radius of rotation decreases. And as a consequence, its velocity has to increase. That causes it to be redirected to the right because it starts moving faster and faster and faster. Now this might be hard to think about in some respects, but it's pretty easy to think about if you imagine a figure skater. So to conserve angular momentum, air moves more rapidly as it moves poleward, just like the figure skater himself is going to spin faster as he pulls his arms closer and closer and reduces the radius of rotation. Conversely, air moving towards the equator encounters an increasing radius of rotation. And to conserve angular momentum, it moves more slowly and would be redirected to the right if it's coming from the north. Now there's another force that the authors talk about that's also important, and that's centrifugal force. But really the patterns are the same as the Coriolis effect, and so we're going to skip those for now. This here is a demonstration of what happens as air moves poleward. Air that's moving poleward towards the North Pole is going to encounter a decreasing radius of rotation, and as a consequence has to speed up, and that causes it to move to the right. If it goes towards the South Pole, it's going to also encounter a decreasing radius of rotation, and that causes it to move to the left. Now, if this air simply were to move because the Earth rotated beneath it, you would actually see a trajectory that would look like this, because the Earth itself would be spinning up from out underneath it, and that's actually not what happens at all. Now, knowing that air that's moving towards the North Pole is going to be redirected towards the right, do we actually see this when we take a look at how parcels of air are moving? Let's take a look at the image that we had of Hurricane Katrina again, and if you take a look at the way that this spins, the direction is actually like this. The equator's down here, the North Pole's here, but air that's moving northward actually spins to the left, not to the right. Does that actually mean it's moving the wrong direction? Well, if we actually take a look at what happens with storms, we'll understand that the Coriolis effect is actually causing air to spin towards the left. So storms are areas of low pressure, and that means that's air that's rising. So when you think about air that's rising, that's going to create a pressure gradient. And air has to move from the south and from the north, for example, to replace the air that's being lost as it moves upwards. So from the side, we know that we have in the center of a storm, it's an area of low pressure, and that air is rising, which means that air has to move in from the sides to fill that void. Now from up above, if we draw a circle that represents the rising air in the center of the storm, air is going to be driven pulled in from the north as well as from the south. So that southern air that's coming in still experiences a decreasing radius of rotation. Because of angular momentum, is going to start to spin towards the right. Now the air moving in from the north is going to slow down. So it's going to go and be deflected the direction that we think, to the right. But the consequence of that actually sets up something spinning. So this moves to the right, this moves to the left as far as our vantage point is concerned, and that sets up the spin of the storm that we saw for Hurricane Katrina. If we take a look at another diagram that shows it a little bit more closely, this is a schematic representation of flow around a low pressure area in the northern hemisphere. Centrifugal force isn't important here, and there's really a pressure gradient force that they talk about. So we've got air that's moving in the center of the low pressure system, and you can see that air is coming from the south, and this red is the Coriolis acceleration. So you've got air that's moving in from the south here, and it's going to be accelerated towards the right, which causes it to spin. Air coming in from the north is going to be decelerated, and that's going to move to the right there by its vector, or the left as far as we're concerned, and that sets up the spin. So it actually is the Coriolis effect that causes large storm cells to actually spin in the opposite direction that we might have expected. And so it's true that it's not the right direction, but it is the correct direction.